So today we appeal either to your voyeuristic interest in death or your sense of self-preservation. In a previous lab, you were exposed to this idea of capacitance as the ratio of how much charge is on a capacitor to the voltage across it, so that for a given amount of voltage, if you held more charge, then you would have a larger capacitance. The units of capacitance are farads. That would be 1 farad would be 1 coulomb per volt. You remember that a coulomb is very large in static situations. It's abnormally large. And a capacitor is dealing with static charge, so a farad is also very large. Typically, we will run into capacitances of pico or nano or femtofarads, very small. So here are 3 capacitors, and they are arranged. I hope you would recognize this, that they are arranged in parallel. And what that means is that this plate of this capacitor is going to be at the same potential as this plate here, and at the same potential as these other 2 plates here, that they are all going to be at this high potential, just like that plate. Each of these 3 plates will be the same potential as that. So the thing that is the same for these 3 capacitors is that they all have the same voltage drop. Now, if this capacitor, when it had this voltage of V on it, held a charge of 1 coulomb, and this one a charge of 2 coulombs, and this one a charge of 3 coulombs, I hope you can see that if I were to think about these 3 together as just one equivalent capacitor, that the charge on it would be the sum of 1, 2, and 3, or there would be 6 farads on this capacitor here. Now take this sum, go back to this definition of here, and wherever you see Q, replace it with C times V. So this would be C equivalent times V equivalent. This would be C1 times V1. But then, recognizing that the voltage is the same for all of them, you come up with a statement about what this equivalent capacitance is relative to these 3 capacitors. Now I have them in series, one after the other. And this is not much of a circuit. You can see it has holes in it. It's no circuit at all. But if there was a switch here, when you closed the switch, electrons would leave this plate and flow to here, so that this and this had the same potential. Similarly, electrons would flow off of this low potential end of the C to V MF onto here, causing these 2 to have the same potential. But as the electrons leave here and the charge on this plate grows, there will be an electric field which also grows. And that electric field will induce a negative charge here, and the way you get that negative charge is by stealing electrons off of this plate, which means this will come to have a positive charge, which will create a field, which will induce a negative charge here, positive there, and ultimately what you end up with is these 3 capacitors being charged. Even though you had these floating elements, the charge rearranges because of the fields, and each of them will have the same charge. You may have to take that as an item of faith, but it is true that capacitors in series all have the same charge. Remember that for resistors in series, they all had the same current. So instead of charge per time, this is just charge. It's very similar. Okay, now what we want to get at is what is the equivalent capacitance of those 3. And again, the question is that we've already established what is the same for all of them, And then if we consider voltage, well, we'll do a Kirchhoff around here. You gain voltage there, but then you go from high to low. That's a voltage drop, a voltage drop. And those three voltage drops, that is V1, V2, and V3, must add up to V. So this voltage drop across those three, the equivalent voltage drop, would be the same thing as the sum of the individual voltage drops. Again, take that sum, V equivalent is equal to V1 plus V2 plus V3, and go back to that formula, C equals Q over V, and replace each of those V's by its equivalent, which would be, you bring the V over here, it would be Q divided by C. So it would be Q equivalent divided by C equivalent is equal to Q1 over C1 and so on, plus, plus, plus. Then take out the equal parts and you get a statement about the equivalent capacitance as a function of those three capacitors in series. And I would hope very much that what you arrived at is that when they are in parallel, that you just add them up to get the equivalent capacitance. But when they're in series, you add their reciprocals to get the reciprocal of the equivalent capacitance. This is, of course, the opposite of what went on with resistance, where parallel resistors you were adding reciprocals and series resistors you were just adding them up straight. And now, just like we did with resistors, I want to do this kind of a problem where you have a mixed circuit. And of course, what you do with a mixed circuit is to look for pure parts. Here is purely series, so we'll start with that. And they are in series, so you add reciprocals. 1/6 and 1/3 is 1/2, but that's the reciprocal of the equivalent resistance, so the resistance across those two is 2 farads. But that 2 farads across here is in parallel with 1 farad, and so you just add them up and you get 3 farads, and that would be the equivalent capacitance of this circuit, would be 3 farads. Now, if you know the capacitance and you know the voltage being dropped, then you can get what the charge is. You just go back to this formula here. You put in 3 and 9, and so this would be 27 coulombs. Find the charge on the 1. Well, what you need to realize is that that is in parallel with this other. And so in parallel, what is the same for both is voltage. That 9 volts will be dropped. Come back here. Its capacitance is 1 farad. 9 volts is being dropped. So that is going to be 9 coulombs is the charge on that one. And the charge up here, well, it's going to be the same charge there, there, and on the equivalent. And what the equivalent capacitance was across the top was 2. So you have 2 farads, 9 volts being dropped. That's going to be 18. That is 18 on this capacitor, and 18 on this capacitor, and 18 across the equivalent of those two. And of course, we talked about the fact that if there's 27 here and 9 of it is here, then the remaining 18 must be here. Find the voltage of these two. Look at them, see that they are in series, and what's the same in series is charge, so you want to work with that. That each of these two have 18 coulombs. So 6 farads, 18 coulombs, that must be 3 volts, and 3 farads, 18 coulombs, that must be 6 volts. And so you have done that problem. I hope you find that fun. I hope you were looking forward to doing more like that. Nice little puzzle to untangle. Okay, shifting gears, I want to talk about the use of meters. And here I have this circuit, and as it stands with this 30 ohms and 300 volts being dropped across 30 ohms, I know that there are 10 amps flowing, but suppose I wanted to measure it. Well, then what I'm going to have to do is put an ammeter into this circuit. Very important that you understand that an ammeter does not hover over this resistor. It doesn't look at this resistor. An ammeter doesn't tell you what the current there is at all. What an ammeter tells you, get this, is the current through it. So all this is going to do is say, here's the current through me. I want that to be the same as the current through the 10 ohms, and so I need to put it in series so that the current through here is the same as the current through there. I can read that and know what it is. But suppose this ammeter had a resistance of 30 ohms. By adding that to the circuit, I would go up to 60 ohms here. Now there would be 5 amps flowing. There would be 5 amps here and 5 amps there. Yes, it would be telling me the current there, but that's not what I want. I wanted to know what was the current there before I added the ammeter. And so, to not change the circuit when you put the ammeter in, what you need to do is to make it invisible to the circuit. It's like if I was a zoologist and I wanted to see how animals behaved, but the animals could see me. Then they would behave the way they do when there's a zoologist around, not the way they do in nature. So I have to make myself invisible so that they will behave normally. I have to make this ammeter invisible so it doesn't change the behavior when it comes into the circuit. That is, I want that ammeter to look exactly like the wire that was there before I put it in. I want the ammeter to have very low resistance, not 30 ohms. I want it to effectively have 0 ohms resistance. And that is the design of an ammeter. Because it is used in series, because it is used in series, you must make it have low resistance so it doesn't change the circuit. And now for the voltmeter. The voltage being dropped here is 100 volts. And I want to take a voltmeter and find out. But again, the voltmeter is only going to say, here's the voltage being dropped across me. And I want that the same as the voltage there. And so what I need to do is to hook up that voltmeter in parallel. So its voltage drop will be the same as the voltage drop where I want to take the reading. But again, if the voltmeter had a resistance of, say, 10 ohms, then the equivalent resistance here would become 5, and the circuit would have 25 ohms instead of 30. The current flowing would be different. So instead of 10, the current flowing would be 12. It's not good. When I put this in, I don't want to change the circuit. And so just like with the ammeter, where I wanted it to look like a wire and have very low resistance, I want a voltmeter to look like what was here before you put the voltmeter in. And what was there was nothing. It was air. And air has very high resistance. And if that voltmeter has very high resistance, when you put it in parallel with the 10, you're going to have 1/10 plus 1 over a very large number, which is going to be about the same thing as 1/10. I won't have changed the resistance of the circuit. I won't have changed the behavior of the circuit. This is the multimeter that you work with. And note that when you turn the dial over to this part that you're reading voltage, all you're doing is turning this into a very high resistance device. And when you put the ammeter over here, so you're measuring current, all you're doing is turning this device into a very low resistance thing. And of course you hook them up differently, whether it's being a voltmeter or an ammeter. But essentially the difference between a voltmeter and an ammeter is how much resistance they have. Here we are, back to that puerile interest in body damage. That there are several equivalently bad ways that electricity can damage your body. That your nervous system runs on electricity, so electric current will override or mess up your nervous system. In particular, if it goes through your brain, it will change the information that's moving around in your brain. And one of the common effects of being shocked by electricity is for people to stop breathing. You have to resuscitate them. If it goes through a muscle, it will cause the muscle contract. That's how your brain controls your muscles. It sends electric shocks to them, and that makes them contract. Well, this very large current going through your muscles causes violent contractions, which can break your bones and rip muscles loose from the bones. That there used to be an ad saying, "Don't dig without calling the electric power company," because electric shock was like getting hit by a truck, and that's what they're talking about. Another thing is that because of the current flowing through the resistivity of your body and your body organs, you will get burns. And your heart sends, your brain does not tell your heart how to go. It's got a built-in kind of nervous system that one chamber of the heart fires, and it sends a signal to another part of the heart that says, "Okay, now you fire, I'm done." And then that one sends a signal back and says, "Okay, I'm done, now you fire again." And so the heart parts talk to one another and they fire in order. But if an electric shock goes through your heart, it will change that into a chaos instead of this regular rhythm. That's called fibrillation, and it's very bad thing. And the treatment for it is actually to hook up these paddles and send an enormous current, and the person jumps off the gurney because all the muscles in their body contract, but in particular the heart muscle contracts so much that it stops. And then the hope is that when it starts again, it will start with a regular rhythm. So that's what that defibrillator is all about. Finally, here is just some numbers I got off the internet. To feel electricity, 1 milliamp if it's AC, it takes much, much more. Your body is not as sensitive, nor is it as damaged by DC. The let go threshold, that means at 10 milliamps, your brain can no longer tell your muscles what to do. You're holding on to a live wire, it's burning you, it's hurting, and your brain's saying, "Well, let go of it, you dummy." And you can't, because the electric signal from the live wire is stronger than the signal from your brain, and you do not have control over your muscles. This heart going into fibrillation at 30 milliamps AC, that's if it's on the skin. If it gets inside, like directly on the heart or just inside the body, then a 1/3,000th as much current will cause the heart to go into fibrillation. Finally, I want to talk about grounding. That if, this person shouldn't have been having a radio next to the tub, but if they he reaches up with his wet hand and touches this box or touches the knob, and it's live, that is, there's electric current flowing to it, then the current will have a choice of going back through this wire to the low potential or going through his body to the low potential of the earth. This will kill him. And so the safety measure is to put this third wire on here. It's on your plug, it's the thing that's connected up to this hole here. And that from this hole, there is a pathway that goes into the ground. So if the outside of the radio or the knob were to become live, if this has been wired correctly, then the current would flow to the knob and then to the ground wire, and immediately there would be a short circuit and the breaker would trip. But even if that didn't happen, even if the breaker didn't trip immediately when you plug in the radio, if when you put your wet hand up here, that finally caused the outside to become live, at that moment there would be a choice of going through you or going through this wire, and you would be protected by the fact that it would choose to go this way. Thank you.